All right. So the first, stop talking, please. The first half of chapter 8, we're going to be talking about two-dimensional vectors. This half is, I think, more familiar anyways, since we've done a little bit of these kinds of calculation before in first semester, so this should ring a little bit familiar. But there's a lot of vocab here in chapter 8, especially the first half of chapter 8, that becomes really important in both understanding what's going on and being able to answer the kinds of questions that we're going to ask you to do later on. So we're going to start with some definitions here. So a vector is a pair of real numbers which represent the magnitude and direction. So a vector is a new kind of quantity. So a vector quantity contains both information about a magnitude and a direction. It needs to be able to describe both of those two things. Represents. So we can represent a vector in a couple of different ways. So we can represent a vector just as two numbers, a magnitude and a direction. For example, we did some vector problems in first semester. So if I have a 20 mile per hour wind with a bearing of like 80 degrees, this is like my magnitude, that's like my direction, but that's a description of a vector just as a magnitude and a direction. Next is as a component form. So for example, maybe, or the way we denote a vector in component form is we use the two wedged brackets, and then we'll write like an ordered pair there. So we can represent a vector in component form. So in component form, we're assuming the initial point of my vector is 0, 0, and the terminal point of my vector then is the coordinate point AB. So in particular in this chapter, it's going to be very important that we're using our notation correctly. So there's a big difference between the parentheses AB and the wedged bracket AB. One of them is a point, the other one is a vector. So we have to make sure we're being quite careful about how we're using that notation so that we're able to kind of keep these ideas straight. Why would do that? So another way we can represent a vector is with a pair of points. So say we have point A, which is x1, y1, and point B is x2, y2. Then we can talk about the vector like AB or BA. So one of the things that we do to help us differentiate a vector quantity from just a scalar quantity, like just a regular real number, is when we write a vector symbol, we put like a little arrow over the top of it to differentiate between like a variable and a vector. And if you're writing a vector with a two-letter notation like this, the order of the two letters matter. So the vector AB has an initial point of A and a terminal point of B, as opposed to the vector BA, whose initial point is A and its terminal point, or its initial point is B and its terminal point is A. Much in the same way you named rays back in your geometry course, right? Should look a little bit familiar. It's the same kind of naming convention. So and the fourth way we'll deal with here in this chapter is talking about a vector geometrically. So in a geometric setting, if I talk about the vector AB, I'm going to have a arrow that has a beginning and an end. The point of the arrow is indicating the direction, and the length of the arrow is indicating its magnitude. So these are four different ways that we can kind of denote a vector. And most of what we're going to be dealing with in this first section is talking about ways to kind of move back and forth between these different forms. So we've been using this word magnitude for quite some time. So if we talk about the magnitude of some vector v, notice here when I wrote my vector symbol for v, I put the little arrow hat on top of it. In a text, you'd either see the arrow hat on top of it, or oftentimes you'll use a boldface on the character v to indicate that it's a vector quantity as opposed to a scalar quantity. That's what your notes that I posted to PowerSchool have, the typed out notes. Just so you know, when you're reading that, when you see the boldface letters, those are representing a vector as opposed to a scalar. We denote the magnitude of vector v. We use the vertical bars around the vector v to indicate a magnitude. Notice that this is, I think, probably the third different time we've used this vertical bars notation to represent something. So in the first time you probably saw these vertical bars, they were representing what? Absolute value, right? And last year in your algebra course, we also saw these vertical bars could represent the determinant of a matrix. And this is now a third time we're going to use these vertical bars to represent something, this time a magnitude of a vector. Okay, so there's 3 different times we've used this notation. Now, don't be confused. There is no such thing as the absolute value of a vector. There's no such thing as the absolute value of a matrix. You can't take the determinant of a real number. You can't take the determinant of a vector, etc., etc., etc. So these should be clear from context which symbol or which notation or which operation those vertical bars are representing. Okay. We also had said that a vector has a direction. So the direction of a vector v is the direction the arrow points using angles in the standard position on the xy axis. So for example, if I have, say this is my vector v, actually I'm going to draw it this way. What I can do is put in like an imaginary xy axis, where the initial point is the origin of my imaginary xy axis. And this standard position angle here then would represent the direction of this vector. And we spent a good deal of time in first semester talking about how you can calculate things like that, right? So that should be something that's a relatively familiar task. Okay, so we have all these different representations for a vector, and there's still some more that we'll see a little bit later in this chapter. Why do we have all these different representations? Well, it turns out that they're good for different things in different contexts. From a practical standpoint, doing computations, component form is often going to be the most valuable form to have our vector in because it's quite easy to manipulate a vector or combinations of vectors when they're in component form. Magnitude and direction are often helpful in terms of communicating information. They often have a lot of good real-world value. In practical terms, they're easy to work with. Geometrically, it's often very easy to get some intuition about kind of what's going on It's easy to look at a picture and understand the situation, so the geometric perspective is nice. And this pair of points is easy to create a vector from a pair of points, right? It's a very easy description to generate on your own, although working with that description is not tremendously easy. So one of the things that we're going to be particularly interested in is going to be getting things into component form and getting things into magnitude and direction. Now, oftentimes we're going to want to put vectors into component form so we can do some calculation, and then we'd want to be able to get vectors out of component form and back to magnitude and direction to express a final answer. Sure. So the first conversion that we're going to talk about is going from a pair of points to component form. And to do that, we do what's called the head minus tail rule. So if our initial point or tail of our vector is x1, y1, and the terminal point of our vector or head is x2, y2, then our vector in component form is going to be head minus tail, comma, head minus tail. So just to kind of demonstrate to you what we're doing, say this is our vector here. What we want to do is we basically want to perform a translation and move this vector so that its initial point is at the origin, right? What type of transformation involves just picking it up and moving it? That's a translation, right? So how far to the left do we need to move this? We need to move it there and then there, right? Everybody agree with that? Well, that's x1. And that's y1, right, as those quantities. Everybody agree with that? So when I perform that transformation then, when I subtract x1 and y1, because we're moving left and then down, this point would become 0, 0. And when I do the same thing here, this point becomes x2 minus x1, comma y2 minus y1, right? So all this formula is just us translating our vector so that the initial point is now at the origin. Everybody okay with that? Okay. Next thing I want to talk about are equal vectors. So for two vectors to be equal, what has to be true? means they have to have the same magnitude and same direction. So if this is my vector v and my vector u, do these look equal to u? Yeah, they eyeballishly look equal, right? What's one way we could check to see if they're equal? Okay, that'll just tell me if the magnitudes are the same. What if I compared their component forms? If they have the same magnitude and direction, what will their component forms be? The same, right? Because if I go and I translate this one down and over, and I translate this one like up and over, if they're the same, they'd be in the exact same spot. They'd have the identical component form. So that's going to be probably the easiest way to check to see if two vectors are equal, is to just compare their component forms, right? Because what do we have to do to convert a vector into component form? It's very easy, right, to get things into component form. We just subtract their terminal, or from their initial point from their terminal point. Or if we're given magnitude and directions, we'll see a bit later how to do that, and that's also quite easy. Is everybody okay with that as a method for checking to see if two vectors are equal? Obviously, you could compare magnitudes and directions, but those calculations are going to be a little bit more difficult, right? Just calculating the distance between 2 points is a little bit more cumbersome than putting something into component form. Okay. So if I have a vector whose initial point is A and the terminal point is B, and I want the magnitude for my vector AB, if the magnitude is just the length, I can just apply the distance formula, right, which you probably recognize from your geometry course. Or your Algebra 1 course, you probably saw it there also. But what happens if I have just a vector that's in component form? What does this magnitude formula simplify to now? Why is that? In component form, what's the initial point? It's the origin. What's the terminal point? It's the point AB. So when I plug this into my formula up above for the distance, I'd get b minus 0 squared plus a minus 0 squared or I'm sorry, a minus 0 squared plus b minus 0 squared, all square rooted, right? Which just cleans up to be a squared plus b squared, all square rooted. Do we feel okay there? So you could either, if given 2 points, use the distance formula, or you could convert them to component form first and then use the component form or magnitude formula. You're doing the same thing either way. Everybody okay there? Okay. So what if we want to calculate a magnitude and direction? So we have a vector v whose initial point is 3, -3, and whose terminal point is -5, -10. I would start by translating this information into a vector and component form. So I'll do head minus tail and head minus tail. Which gives me -8, -7. Everybody happy there? Now that my vector's into component form, it's quite easy to take or to find the magnitude. Everybody okay there? And then to find the direction, I'm going to do this just like I would have in a first semester problem. So I'm going to plot the point -8, -7. And what I'm looking for is that angle, right? So to calculate that angle, what I'm going to do is I'm going to draw a reference triangle whose side length is the value for x and the value for y. And that's going to allow me to calculate this angle that I'm going to refer to as alpha. That angle that the vector forms with the x-axis. So if I use tan inverse, I can do opposite over adjacent. And then theta would be 180 plus alpha, right? So when I type this into my calculator, I get 41.19. So this one is 221.19. So this was a good example of us taking a vector that's in point form or component form and translating that into a magnitude and direction. What if I want to go the reverse direction? What if I want to go from a magnitude and direction into component form? And maybe we could write that in here above this example also. So this was 2 points / component form to magnitude and direction is what this example basically showed us, right? Okay. So let's imagine what we are trying to do here. Oh, I'm sorry. This is the, yeah, that's what I want. Okay, sorry. So let's say here's my vector v. Everybody's okay there? Actually, let's start this way. My vector v. I can draw in an imaginary xy axis here, whose origin is at the initial point for my vector. So to figure out the component form then for vector v, I need to figure out the side lengths there for that triangle. I need to figure out the A and the B. Everybody's okay with that idea? Now there's one other piece of information here that I haven't drawn, or some other piece of information I haven't drawn in yet. I know that that is my angle, and I know that side length, the length of the vector. So what is this going to mean? A is the adjacent side of that triangle, and B is the opposite side of that triangle. And by using theta as opposed to that angle inside of the triangle, what does that do for me? Because I'm using this angle as opposed to that angle there. What's that, Lindsay? We'll give you the direction, but why am I using theta instead of that acute angle inside of my right triangle? Let me clarify. I don't think I was very clear as to what I was really fishing for. What's the advantage of using theta there as opposed to that acute angle inside of our right triangle? Beyond that, just we already know what theta is. It has another decided advantage. It's going to give you the correct sign on our A's and B's, so we don't have to remember to change that based on the quadrant that they lie in. If I'm using the acute angle from the right triangle, then I'd have to go back and look at what quadrant I'm in and make sure my x and y coordinates are positive or negative where they would need to be. But by using the theta there, I know that cosine theta, for example, is negative in the second quadrant automatically. So that sign is going to be carried with me when I convert it into component form. So it's very nice. It allows me to not have to think too much about what's going on. I just put in that direction and just forget about it. The signs take care of themselves. Becca?
Under, in like the blue and the arrow, is that like the sign for vector, like in the triangle, under like the red line?
That's me drawing in the magnitude of vector v. So let's look at a quick example here. So let's write the component form for vector v with the magnitude of v being 5 and the direction is 224. So I'll just use the formula that we developed earlier. So I have 5 times cosine of 224, comma 5 times sine of 224. And when I type that stuff into my calculator, I get negative 3.60, comma negative 3.47. So we're going to start talking today also about vector operations. When I say vector operations, I mean things like addition and subtraction, multiplication. Now, it turns out there's several different kinds of vector multiplications we have to worry about. But we're only going to really look at 2 of those here today. I can't remember if we do the third one when we talk about 3D things later on. I'll have to go and look. So let's again start with some definitions. So the first thing I want to do is denote or define something called the zero vector. So the symbol we use for the zero vector is a 0 with the vector hat on top of it, because we need to differentiate that from the number 0. The number 0 and the vector 0 are not the same thing. What do you think the component form is going to be for the vector 0? Just take a guess. What would you expect? 0, 0. Yeah. So that's just a vector. What's its magnitude going to be then? And this is the only vector that doesn't have a direction. So we've defined one special vector, the zero vector, that has no direction to it. And really we need to do this so that the rest of these vector operations work out in a way that our rules of algebra still apply. Okay, so the next thing we want to do is talk about the sum. Sometimes also called the resultant. So if I want to add two vectors, how do I do that? I can just add them component-wise. So I add the x components together, and then I add the y components together. Very much as we'd hope that vector addition would work, right? Or if I look at this geometrically, if this is my vector u, and say that this one is my vector v, to draw in u plus v, what I'm going to do is I'm going to take my vector u, draw like an imaginary xy axis, and then draw in my vector v, and then if I go then and draw this vector from the origin to the end of vector v, that's my resultant. So geometrically, this is what we're doing. Now to calculate the magnitude and direction of this vector v in green, if I was doing this geometrically, that becomes a rather tedious calculation, right? To get the direction in particular, I'm going to have to be using multiple laws of sines or cosines in order to kind of sort things out there. It's not a lot of fun. That's the power of the component form. As we saw earlier, how easy it is to calculate the magnitude and direction if things are in component form. But physically, this is kind of what's going on. And those of you that are in a physics course now, this should look rather familiar, right? Okay. The next thing we're going to talk about is called a scalar product. This is the first type of multiplication that we're going to talk about today. When I use the word scalar, I've used this a couple of times now. Do we know what we mean by scalar? A scalar is just a real number. So a quantity that's not a vector quantity, that's just a number, is often referred to as a scalar. So if I take a scalar and a vector, the scalar times the vector, well, that product is just going to be done component-wise. So I just multiply the scalar to each of the components of my vector. So again, from a geometric standpoint, if this is my vector u, this would be like what we mean by 3u. So all we are doing is just like stacking u on top of itself 3 times, right? Has the direction changed when we did this? No. What's the only thing that has changed? The magnitude, right? How much is the magnitude changed by? 3 times, right? It's now 3 times as long as it was before. The scalar will only change the magnitude. Correct. It's basically like a scale factor, right? And that's why we use the word scalar here, is it basically scales that vector. If you want to stretch it out or shrink it down, that's what we're doing. Does that feel okay there? So now that we have vectors addition and vector scalars, we can talk about what we mean by an additive inverse. So if you guys remember back to elementary school, if I talk about the number 5, and I want the additive inverse to the number 5, what is the additive inverse to the number 5? You did, you probably just didn't use this vocabulary.
Yeah, we definitely did.
So what do we mean by an additive inverse? We want the number that we add to it to get back the 0. So for 5, the additive inverse is -5. So if I have the vector 3, 4, what's going to be the additive inverse of the vector 3, 4? -3, -4. Because when I add the vectors, I add them component-wise, right? So if I have the vector u, then the additive inverse then would be -u1 and then -u2, right? How am I going to denote that vector? I'm going to write it as -u. Because what other number is there out front with it that is there but we didn't write down? A 1, really. This is -1 times the vector u. Is everybody okay with that idea? Okay. So now that I have that, that allows me to define vector subtraction. Because just like for real numbers, we can think of subtraction as adding the negative. We can do the same thing for vectors. Okay. Is everybody okay there? Here's a quick question. So we noticed when we did scalar multiplication, we multiplied by a positive number. The direction didn't change, but the magnitude did, right? Yeah. If I multiply by -1, what's going to happen? Is the magnitude going to change?
No, just the direction.
The direction will change. How much will it change by? Let's look at a picture here and kind of think about that. So here's this one. Yes, that's correct, 180 degrees. Everybody okay with that idea? Yeah, Andrew.
Why do you use the letters U and V? They cannot be.
That's just kind of the convention when talking about vectors. I try to be careful and put tails on my U's. So if you don't see a tail on it, it's probably a V. Okay. So far, so good, right? We haven't done anything super complicated yet.
It's just a lot.
It's just a lot of information.
Is there a step point?
Yeah,
I mean, yeah, and I have, let's see, 2 more things to talk about, and then I'm ready to stop for today.
Okay.
So we say that vector u is a unit vector if and only if the magnitude of that vector is 1. So just like the unit circle has radius, how much? 1. A unit vector has length 1. Okay. So suppose that we wanted to take some vector u and transform it into a unit vector. So let's say we want to find a unit vector that I'm going to refer to as u that's in the same direction as the vector v. So geometrically, what I'm trying to do here is if this is my vector v, that's going to be my unit vector there. Is everybody okay visually what it is that we're trying to do here? So I have some vector v. I want to keep the direction the same, but I want its length to move down to so it's 1 unit. If we're changing the magnitude but not its direction, what are we going to need to do? Scalar multiplication. Very good. So the question becomes, what do I need to multiply vector v by then? What is it that I'm going to be having to multiply vector v by? So if vector v has a magnitude of 5, it would need to be 1 over 5, right?
Wow.
Yeah, that's what I said. I said 1.
So we just multiply by 1 over the magnitude of that vector v. Yes, sir. Mm-hmm. Does it seem like I enjoy it?
It does.
Okay.
We don't seem to enjoy it.
I think we go back to the last chapter.
Last chapter was so easy, though.
Right.
Exactly.
Let's keep it that way. This is like.
Okay. Everybody take a deep breath. Take a deep breath. So this is not, right now, nothing we've done is very complicated. You've had a lot of notation and a lot of vocabulary thrown at you, and you feel overwhelmed right now. That's okay. That's normal. That's normal. It's okay. Okay? When we sit down and you guys work on the homework tonight, the homework shouldn't feel tremendously difficult because none of the computation is difficult to do. What you're going to need to do in the homework is sort out like the directions and the vocabulary. So it's like, oh, when it says, this means that, okay, I just need to do that. And none of the steps that you're going to be needing to do on the homework are difficult steps. They don't take a long time. They're not very hard to do, but you have to get used to the vocab, and you got to familiarize yourself with the notation so you get comfortable with those things. And it's not really that bad. Why it feels bad right now is because of the amount of notation and vocabulary got thrown at you in one day. So let's find, here as an example, let's find the unit vector in the same direction as v. Okay? To do that, I need the magnitude of v. So my unit vector in the same direction as v should just then be 1 over the square root of 61 times the vector 5, negative 6. So to do that scalar multiplication, I just multiply 1 over the square root of 61 to both the x and y component. Now, this is probably not the way we want to leave our final answer. What's wrong with this? Yeah, the square root in the denominator. So how do we fix that? Yeah, just multiply the top and bottom of each fraction by the square root of 61. And that's it. So again, not a difficult calculation to do. It's just getting familiar enough with the vocabulary and the directions so you know what to do, right? Okay. The last thing I want to talk about today, just relax.
I think that was a really good stopping point.
This is the really good stopping point because this connects directly to the previous. So the standard unit vectors are vector I, which is the vector 1, 0, and vector j, which is the vector 0, 1. These two vectors are important because they allow us a fifth way to describe a vector. That is with a linear combination form. So for example, let's say I have the vector v, which is the component AB. Okay. I can rewrite this as the vector A0 plus B0, right? Everybody agree with that? That's just basic vector addition. And I can rewrite that first vector as the scalar A times the vector 1, 0. And I can rewrite the second vector as the scalar B times the vector 0, 1. That's just basic scalar multiplication, right? Now the vector 1, 0, we have a special name for it. We called that vector vector I. And the vector 0, 1 we have a special name for. We called that the vector j. So this is our standard combination form. It basically just is rewriting our vector as the sum of two unit vectors. Okay? That's it. This is where I'm stopping.
Wow. Wait, you scroll up
Yeah.
for one.
I have problems.
Of course.